In this problem, we are given that in triangle ABC, AC equals to B, AB equals to C, BC equals to A. AD is a line such that D is on BC. CD equals to N, BD equals to M. Prove that A times D squared plus MN equal to MB squared plus NC squared. This relationship is known as Stewart's theorem. The desired equation has multiple squares of side lengths. And in geometry, when we have squares of sides, there's two types of theorems that come to mind. The first one is the Pythagorean theorem, but we cannot use that because it requires right triangles. The second one is the law of cosines, and we can try using that to prove this theorem. You have to apply the law of cosines to both triangle ABD and triangle ACD, since we need equations involving M, N, and D. And we can focus on the angles ADC and ADB because these angles are supplementary, which allows us to easily relate their cosines. The cosine of angle ADC equals to the cosine of 180 degrees minus angle ADB. By the properties of cosines, this will equal to negative cosine angle ADB. To prove this, you can just expand the parentheses because by the identity of the subtraction of angles for cosine, you will get that cosine of 180 degrees minus angle ADB equals to negative cosine angle ADB. Then, from the law of cosines, we have cosine of angle ADC. This will equal to D squared plus N squared minus B squared divided by 2dn. Cosine of angle ADB equals to D squared plus M squared minus C squared divided by 2dm. Therefore, cosine angle ADC equals to negative cosine angle ADB. This will give us D squared plus N squared minus B squared divided by 2dn equals to negative D squared plus M squared minus C squared divided by 2dm. We want to remove the fraction, so we can multiply both sides by a common denominator, 2dmn. This will give us D squared M plus mn squared minus B squared M equals to negative D squared N plus M squared N plus minus C squared N. Rearrange this equation will give us D squared M plus D squared N plus mn squared plus M squared N equals to B squared M plus C squared N. And they might have factored this to get into a form that is similar to Stewart's theorem. D squared times M plus N plus Mn times M plus N equals to B squared M plus c squared n. Now notice that m plus n just equals to a. So we can factor that out. So a times d squared plus mn equals to b squared m plus c squared n. And that is how you prove Stewart's theorem.